Does the way we route tokens in a mixture of experts model actually matter? In the current AI landscape, we're seeing an arms race of routing topologies. We have multi-hop trajectories, hierarchical gating, and complex chains of experts. The implicit assumption is that a more sophisticated routing mechanism leads to a more capable model. But a recent research paper titled Equifinality in Mixture of Experts asks a provocative question. Does the routing topology actually determine language modeling quality, or are we over-engineering the plumbing? To answer this, the researchers developed ST-MOE, or Semantic Trajectory MoE. Instead of the standard linear router, which is essentially a large weight matrix, ST-MOE uses geometric cosine routing. It projects tokens into a low-dimensional space, just 64 dimensions, and routes them based on the cosine similarity between the token and learned expert centroids. This isn't just a minor tweak. This approach uses 80% fewer routing parameters than a standard linear router. To see if this efficiency comes at the cost of quality, the team ran 62 controlled experiments on Wikitext 103, training models to full convergence. The results are striking. They found what they call routing topology equifinality. They tested 5 different cosine routing variants, ranging from wide architectures with a single hop to deep architectures with multiple hops. After training to convergence, all 5 variants landed within a tiny perplexity band of less than 1 point. Using the 2 one-sided tests framework, they proved that these topologies are statistically equivalent. Essentially, whether you use a single-hop wide route or a complex multi-hop trajectory, the final language modeling quality remains almost identical. Now you might ask, does that mean the router doesn't matter at all? Not exactly. When they compared these to a standard linear router, the linear router actually performed better. However, there was a catch. The linear router had over 5 times more routing parameters. When they increased the capacity of the cosine router to match the linear one, they closed 67% of that performance gap. This reveals a critical hierarchy in MoE design. Routing capacity matters most, followed by the routing mechanism. But the routing topology itself, the actual shape of the path the token takes, is almost entirely neutral to the final quality. So why does this happen? Why do structurally different topologies converge to the same result? The researchers found a mechanistic explanation they call the echo chamber. By measuring the cosine similarity between updates across different hops, they discovered that multi-hop updates are highly collinear. In plain English, the model isn't using multiple hops to perform complex compositional reasoning. Instead, it's using them for magnitude amplification. It's just hitting the same direction over and over again. They proved this by replacing the entire multi-hop structure with a single learnable scalar, and the performance stayed virtually the same. This leads to a very practical payoff. If the routing topology is quality neutral and the updates are redundant, we can use geometric halting. By implementing a zero-shot relative norm halting mechanism, the researchers were able to detect when a token's update had effectively converged and stopped the trajectory early. This saved 25% of the MoE flops, with a negligible increase in perplexity of only 0.12%. This is a massive win for inference efficiency, and it works without any retraining. The paper also touches on architecture dualism. They found that if you have many tiny experts, the microregime, a deep multi-hop topology, is slightly better. But if you have a few large experts, the macroregime, a wide single-hop topology, wins. This suggests that the optimal topology is actually driven by centroid density in the routing space, not by some inherent magic in the multi-hop design. To wrap this up, the takeaway for AI researchers and engineers is clear. Stop obsessing over increasingly elaborate routing topologies. The ceiling of your model is set by the expert pool and the routing capacity, not the specific path the token takes to get there. If you need raw throughput, stick with standard linear routing. But if you want a model that is transparent, easier to analyze, and capable of adaptive compute through halting, geometric routing is a powerful, parameter-efficient alternative. The bitter lesson here is that the expert weights are incredibly flexible. They will co-adapt to almost any routing mask you impose on them. In the end, the experts do the heavy lifting, and the router is just the usher.